Alright, so hello and welcome. Howdy. Another problem, integer to English words. Hoping this is not also MySQL. Here's the hoping. Yeah, let's get right into it. Let's get right in the news. Let's get right into it. Okay, convert a oh, that's a lot of downvotes. Oof. Non-negative integer num to its English words representation. Okay. Make you regret you ever lived. You want to be a programmer? I'm just kidding. Right. So this is kind of an obnoxious question. They just gave it a hard. They're like, it's hard. This is hard. 123. So there's no ands. I noticed there's just 123, 12,345, 1,234,567, 1,234,567,891. Yeehaw. Oh, this is obnoxious. See why there's so many downvotes. I just don't want to do this. It's flat out. I'd rather not. I really just prefer not to. What are some expected values? Let's start with that. Like, let's go through, like, what do they even expect? I don't know. We can just pick some random numbers. Let's go from 0 to, oh no, wait, actually have to do it this way. I don't even know what they're expecting here. It's like 10,000 different numbers. See if we see any numbers that we really didn't think would work. I guess we could, I don't know. I don't know. Let's go like a million to like, let's go like 50,000, 5 million. I don't know, 500,000. Oh, we don't, okay. 995,000 to, alright, that's probably not good either. Let's do, It's really awkward with the numbers. Like, if you're trying to pick random numbers in a very large range, the probability that the number is going to be towards the higher end of that range is a lot higher than it'll be. Like, if you split like a million numbers, right? And you split them into numbers larger than 100,000, numbers larger than 10,000, numbers larger than 1,000, numbers larger than, etc. Right? You go sort of intervals of a logarithmic scale. The probability that your number, if you pick like 1,000 numbers, the probability that your numbers would be in the above 100,000, because that's 90% of your range, is basically 9 times higher. It's very likely you're going to have numbers over 100,000 if you pick between a million. Same deal if you have between 1 and 2 billion, roughly 2 billion, which is what we're doing here. It's very likely 90% of your numbers are going to be over 200,000 or 2 million, something like that. Yeah, so that's really awkward. Anyway, I'm just thinking, like, what do we even do here? I don't know, man. I don't want the 5. Oh, let's do like 100. 100, even 100 is so many. 3, 4, 5, 6, and we just do. It's a lot, man. It's a lot. What do they expect? That's what I want to see. That's what I want to know. What do they want from me? What is the expectation? What do you want from me? 999,950. Oh, that is so awkward. 999,950. How about like when we get to a million? 999,999. So 90. 1 million. 1 million. 1 million 1, 1 million 2, 1 million 3, 1 million 4, 1 million 5, 1 million 6, 1 million 7, 1 million 8, 1 million 9, 1 million 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 29, 40, 1,049,000. This is obnoxious. This is so obnoxious. No wonder it's got so many downvotes. This is not a satisfying question at all. It's just obnoxious. Think about this is fun. It's funny. It's so ridiculous. It's funny. Because you gotta go the first like 19 numbers and then 20. So there's the tens, hundreds. You know why they put this in here? This is for all the Indian programmers that have to learn English because they're originally from India, so they have to learn English, and they're just like, how about you? How about you English speakers? Take a moment to appreciate how ridiculous it is to actually write out the number, what the rules are. Yeah, I don't know, man. I learned the rules when I was a kid, and I just memorized them, I think. All right, so yeah, because you want like an algorithm, right? Like that's the idea. Basically, there's some kind of an algorithm to this. How does it work? It's the digit place, and then tens have their own, so 10, 20, 30, 40, 50, 60, all the way up to 90. So tens have their own numbers, or their own names. The digits have their own names, 0 through 9. You also get names for 10 through 20, 11, 12, 13, 14, 15, right? The teens get their own names. But you don't say 1100, right? You'd say 1100, right? So it's only the teens, the numbers themselves, that get their own names. But you do get 1300 or 1313. You do get that. 1000, so it's like 1113 or 1000. Yes, do 1113. Right, that's not going to be 1113, which is what I like to say from time to time. Just technically incorrect and just so confusing. Yeah, I started doing that. Like 1250. Yeah, 1250. 1250. Yeah, 1113. Yeah. So that stops after the first two digits. So I guess you just need to check if it's a teen number or not at the end. And then all the numbers in between, so 1,000, 100, how about 10,000? What does that look like? If we do 11,000, but then it gets awkward again. You get 11,113. How about that? It actually is 11,000. It's not 10,000 plus 1,000. Yeah. So every factor of 3, you got to revert back to the rules. Oh, that's so obnoxious. Oh, that's great. That's a lot of fun. Oh boy. So the way it works is there's hundreds. But now what if you do 1100,000? So 111,113. How about that? That was 111,113. So each, so 1,000 million billion separate every third chunk, but you can recurse on those chunks. For the 0 through 999, it follows the same rules. So you go back to 111,113. Oh, dude, that is the most obnoxious thing ever. Who made this stuff up? Who came up with this? Who did this? Why? Why did you do this? Oh boy, I'm not gonna get this right either. By the way, there's no way. There's no way. There's gonna be something I get wrong. So you can write. All right. So which parts can we reuse? The parts that you can reuse are the parts from 0 to 999. You can break that up into the first, the last 3 digits, what that reads off as. Then you put 1,000 in front, and the next 3 digits you could reuse those chunks every 3 digits. So you could do, like if you had 100 million, right? Let's do 1,100. So we had 1, 2, 3 for a million, 1, 2, 3 for thousands, and 1, 1, 3 at the end, right? So this is 111 million, 111 million, 111,113. And there's no ends. There's just 111 million, 111,113. 100 and 100 and 100 and 100. Right? And that's not a billion yet. We didn't get to a billion yet. When we get to a billion, you do it again, right? So 111,111,113. Oh, that's awkward. So I think what we want to do is write a subroutine that handles the 3 digits. And so we'll put 1,000, million, and then there's going to be a billion for the next set of 3 digits, which you can only have 2, right? That's the limit at the top. So 1, 2, 3, 4, 5, 6, 7, 8. All right, so if we had 2 billion, 111 million, 111,113. Yeah. So we'll do 0 through. We have a subroutine which is under 1,000. So under 1,000, which gives us something. And so every chunk we'll get. So we get 3 digits. So we get A, B, and C. So we do short A, short B. A, short B, and short C. It's actually just a number, really. It should just be a number we get. Under 1,000. And this will be, so then our ultimate algorithm then is going to be, we take the number of digits. So we can say, we'll get the digit set. We'll start with that. I think that's the way to do it. Standard string S equals standard toString of num. We're going to say int d is going to be, we'll say const int digits is equal to s.size. Say d of digits for, we can make these shorts. I'm going to say for int I equals, you could do it this way too. Yeah, okay, I equals 0. So now you got to reverse it. So d of I is going to be equal to, so it's going to be the other way around. It's going to be digits minus I minus 1, or minus 1 minus I. It's more the right way to write it. Of digits plus I, and we're going to say d is going to be equal to s of I minus 0, right? So that gives us all of our digits. So pre-process the digits. So there's another way of doing this using like a modular arithmetic using divisions. You can do it that way too, but this works as well. You can just convert it to a string also if you want. Both are like roughly the same efficiency. I think this is slightly more efficient, but anyway. So now what we want to do is depending on how many digits we have. So the first 3 digits, so we're going to say int, so 4, so we're going to have standard ret string ret. How are we doing on time, by the way? 15 minutes? Okay. For int I equals 0. Not exactly sure how we're going to do this. So we could say, we could start off at like, we want to get the first 3 digits, least significant digits, then the next 3 significant digits, then the next 3 significant digits. I'm going to create a number out of that. So we could do it this way. And we can say int next equals 0, for int j equals I, j is less than I plus 3, and, or j and j is less than digits, increment j. And we're going to say next equals 10 times next plus d of j, right? And now we're going to say ret plus equals, and we have an I, we also have another value. Actually, I don't think you need to increment I here. Oh no, you just say update I to, actually it would increment I by 3. You can increment I here. Oh no, that makes things awkward, huh? Yeah. Yeah, I guess you do it that way. That works too. Plus equals 3. That's fine. So ret plus equals under 1,000 of next. And you want to say, the way it's going to work is you're going to process each, calculate under 1,000, and you're actually going to go from the left to the right. So that's also kind of confusing. So, you actually want to add this to the left side. You're going to build the string left to right, not right to left, which is awkward with strings, I believe. It's a little bit on the awkward side with strings, but that's fine. We can. I mean, this isn't so complicated that we have to do it this way. So actually, it's going to be ret is going to be under 1,000 plus ret, what you already have, plus a string here. And this is going to depend on I, and we're going to say x, start with x, and increment x as well. And we're going to have an array, predefined thousands increments. So we'll just say increment, or just, I don't even know what this, I don't know what these are called, the in-between words, descriptors, called desc, string description, and it's going to be, in our case, we're only going up to 1 billion, so it's going to be 1,000, million, billion. There's only 3 of them. Is that right? 1,000, million, billion. Yeah. 1,000, million, and billion. And actually, you can't initialize an array. Yeah. Okay. So 1,000, million, billion, and that's what x is going to be referring to. So you're going to take this description of x and add that to, so you get the first 1,000, and it's actually going to go, so if red is empty, it's actually going to be the, so this is a little bit confusing. So this is actually very confusing. Maybe we want to go in the other direction, possibly. The first 0 is an empty string, right? You get your 1,000, to the right of it's nothing. The next is a 1. Yeah, so it's actually, these are 4. 0 is an empty string. I mean, these are fine. These are actually usually for characters rather than strings. Okay. So now when you're at 0, it's empty, red is empty, and you get under 1,000. Then you get the next one, you're over 1,000, and so you would add, you compute that and then add the 1,000 there. Same thing for million and billion. Okay, so that's a tricky thing. Predefined thousands increments, and then now we have under 1,000, we have some other predefined values. Predefined number digit names. So we would say digits or digit names from 0 to 9. So there's 10 of these. The 0 is 0. And these are all capitalized, I think. Everything's capitalized. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 8, 9. We actually don't just want digit names. We want predefined names, number names. So we're going to go all the way to, we're just call these names actually. So this is kind of obnoxious because I would prefer to make this some kind of an initialization list. I don't know how to do that with arrays. It can't be default initialized. I don't think you can initialize at all. Can we do initialization list? Yeah, with a dynamic array on not on the heap but on the stack. Yeah, so we can initialize. We cannot initialize. Well, actually, we know these can be initialized because these aren't variable. Oh, I'm wrong. We can't initialize these. That's incorrect. These don't change. If you don't know, if it's at compile time, then you wouldn't be able to initialize it. Excuse me, if it's at runtime, you wouldn't be able to initialize it. So you can do this. I'm wrong about that. That's a subtle thing. Not a subtle thing, but yeah, well, I guess subtle. Yeah, it's fair to say it's subtle. No, I was actually wrong. You can do this. The reason that I thought you couldn't do this is because I'm so used to, if you know what this number is at compile time, then you can do what I'm about to do. But if you don't know that number, then you can't do it the way that I'm about to do it. So yeah, this is wrong. You can do it this way. 0, 1, 2, oops, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. This is going to take a while, huh? 25 minutes so far. 18, 19, 20, and now you get to 21, 22, etc. 1,000 million billion, 0 to 20, and there should be 21 values. Yeah. The 21st is 20. All right, so we have names, and we say if x is less than number names, constants, total names, or 21, or initial names. All right. So if we're less than the initial names, then we just boom, return that. Otherwise, what we want to do is we want to say for more than that, there are another set of names, the initial names, and we're going to call that not just names, but early names or first names. I don't know, initial names, first names. And the next set of names, which there are a few, second names, or second names, I don't know what to call it, first names, second names, smaller names, small names. Call them small names, larger names. I don't know. This is sort of like, they're not ones, they're just smaller. There's 10s, 20s, 30s, etc. Larger names, there are 10 of these. I don't know what to call these larger names. It's probably a better name than that. So let's do 10, 20, 30, 40, 50, 60, 70, 80, 90. Yeah, so there's this next set of names, larger names. This is for the tens digits, tens position. So if you're less than 20, you take one of these. If you're not less than 20, then you're going to take the larger name as a name. You're gonna have three names. You're gonna have you're gonna break this into digits again. So the third digit on the left is gonna be the first thing you add. and that's going to be one of the small names, right? Because it's obviously less than. First thing you add is on the leftmost digit if it exists. If you're, so you have to check, I guess, how big you are. If you're greater than 99, then you're going to parse that digit first. If you're less than 99, less than or equal to 99, or less than or equal to 99, then you check if you're less than. So you could check X immediately. Well, you could do so. Okay, let's do it this way. So this is probably like one of the more core parts of the algorithm, I guess. How are we doing? 30 minutes. Okay, so ret is initially empty. Okay, we'll say if X is greater than or equal to 99, or greater than 99, then we're going to say ret plus equals X modulo 100, or no, excuse me, X divided by 100 of small names, or first names. So take our first names, add 100 to it, 100. Right? If we're going to decrement X by, or X modulo equals 100, right? So remove the first part, so if it's like 800, we add 800 to the front with a space. If X is greater than 21, which is larger names or smaller names, or initial names. So we want to check actually if X is greater than initial names, then we're going to say plus equals a similar thing here, but this is not first names but larger names. And this is going to be divided by 100. So we know we're greater than 20, what have you, so we have something in the tens position. And so we would say plus that, so 100 plus a space plus whatever that is. So it might be a 190, and then maybe there's a 4 at the end, right? So, and then we update here. X modulo equals 10. And finally, we would add at the end here. So now, but here's the thing, is that we might not necessarily want to add these spaces, so that's a tricky thing. We have to kind of consider the spaces. Definitely there's going to be space between this and 100. If X is not equal to 0, then we add a space. I think we add the space here. That means if it's not 0, we know that something else is going to come to the right. So we don't add the space there. So if this is false, let's say it's like 95, then we'll get 90, and then there'll be a 5 here. We're going to say ret plus, and it's going to be the leftover. So if it's 5, first name is a 5. So Now, if we don't enter this block at all, and we get 20, so we get 120, right? Yeah, so this should work for under 1,000. Now the tricky thing here also is the spaces for these 1,000, million, billions. How are we doing on time? 35 minutes, okay. So we get this under 1,000, and we add a descriptor, and then we add ret, and the descriptor could be empty. So, like, let's say we have 1,000, so 100,000, for instance. So you get 100, and then if we need to add a descriptor, we should have a space, right? There'll just be a space. And then whatever we had before, it would just say if x is not 0, we can add a space here too in front of ret. So that's a tricky thing here too. Like, obviously before the 1,000, there's going to be like 8,000, but then we might have a space. There could be no space, right? There should be no space with this 1,000 to the right. Not necessarily. We always know there's something to the left, but we don't necessarily know if there's something to the right. You could even have like 8 million, right? And then, so as long as this value is not 0, you can add a descriptor. So 8 million doesn't have 8 million 0,000 0, right? It just has 8 million. So that's kind of tricky here. It might be better actually just to use modular arithmetic and figure out whether or not we want to add. We could do a similar thing that we did here. I don't really like that though. We could say there won't be anything following if, yeah, I think modular arithmetic is actually better for this. All right, let's do it that way. That's better. That's a lot easier. That's actually a lot easier. Yeah, forget this. We're gonna say I x. Could actually just do I. Let's say t equals num, and we're gonna say t is greater than 0, or well, it could be even equal to 0. I don't know. It's kind of tricky. No, well, the only time you get 0 is, so we could do this. I don't know. Do we want an edge case? We don't really need to do that. This is definitely tricky. Go back to this in a moment. You can do 4 different. This is very tricky. You could do 4 different pieces. Yeah. I don't know. I actually don't know how I want to do this. You run into some issues because you could divide by a certain number, and then you can use modular arithmetic to kind of break part of it down, but that'll give you each 1,000 piece, and you'll also know like which position you are if you're billion, million, thousand. The trick with that though is maybe you just break. Like, when do you stop? And those could be zeros all the way across. you do actually want to process one time. You process the 0. You wouldn't do 0,000. You could do 0 all the way at the end. So we could just have our edge case here. This really should just be the first names. Otherwise, say t equals num. T is greater than 0. You can say p is equal to standard power of 10 to, I think it's a billion is 10 to the 10th, 10 to the 9th. This is where you start. And you say p divide equals 1,000, and t is equal to modulo equals. So what you're going to do is x is t divided by p, right? And then you want to shift p over 1,000 and divide t. You're not going to divide t by 1,000. You're going to take t modulo p, and then move p over 1,000. So when you take t modulo p, you get rid of the billions, and then p goes down to 1,000, 100, millions, and then you take t divided by millions, gives you how many millions you have, and then t modulo p gets rid of all the millions, and now you're dealing with thousands. Yeah, you do it that way. And then t modulo thousands, or excuse me, yeah, t modulo millions gives you hundreds of thousands. And then that gets rid of the millions, and then divide by p again, you're in thousands, divide by thousands, that gives you the 0 to 1,000, and then, excuse me, at some point you get down to 0, but I'm trying to figure out when do you get down to 0? How does that work? T modulo billions gives you the millions. That's after you process billions, you get millions. Then P itself goes down to millions, right? So you divide, that gives you what you want. Then T modulo millions gives you hundreds of thousands. P also will drop to thousands, divide by thousands, and you get divide by thousands, and you get how many thousands you have. And then T modulo P, which is thousands, puts you at just the first 3 digits, and P goes down to 1. So when you divide by 1, you get whatever's there in T. And then finally, T modulo 1 should be 0. And then P also goes to 0. And then you exit the loop. Okay. Well, you're not 0. Okay. That's really confusing. But what you're going to say is ret is going to be under 1,000 of x plus the description of, we could say I starts off at 0. I probably could start off at 4 and then decrement I. Oops. So you start off at the top, and basically we say if x exists, then we can add this portion, right? If there are no to the left side. So if there are billions, then we could add billion, and then if there are thousands, I think we just add a, we also just want to see if, you can do this too, if T, I don't know, modulo P, so that gets a little bit confusing. You want to check if the next part is 0 or not, and so that would be, it's not X, but it's T not divided by P, but if you shift T 1,000 digits to the right, which is actually modulo P, if you take T modulo P, if that's not 0, so if T modulo P is not equal to 0, that means there's more to come. That's really all we need. That means there's another space, there's more to come. Yeah, you just do that. And then, yeah, something simple like that. I realize is like not the most simple thing, but how are we doing? 45 minutes, 46 minutes. And I have a tendency to forget those too. At the end of a declaration, you always need the semicolons. Oh, small names instead of first names? Okay. Call them first names, smaller names, larger names. Refactoring code. Can actually do like edge case. Can even just do like if it's under 1,000. I think this routine will give you that, but this is just a little bit easier. I think there's really only one edge case they really have to handle, which is the 0, but I guess we could do it for all of them. Oh, ouch. Oh, and not X, it's I. Yeah. So it's off at 3, it should be. It's also that minor error. Okay. 113, 100. So the first one's interesting. 113, 111,000, 111,000,000, 2 billion. How'd that happen? How'd that happen? 0, 1, 2, 3. Oh, I think it's, now we're going backwards, by the way. They're going the other direction. I think that might be why. Part of the confusion. 2,111,111,113. These are so close to each other. How are these different? Look at these two. So close. So close. Oh man. How are these different? Maybe this wasn't the one that was different. Oh, we got those right. Okay. Where's the difference? 75. Oh, I see. It's this one. And same deal here. Alright, how do we do? Oh, still wrong. 66, 64. 909, oh, there we go. 909,964. 909,964. 109,964. Should be 90,000, 99,000. Oh, we missed a 90, 99, 999,061. So this one's incorrect somehow. So 60, oh no. 900, so the under 1,000 is not correct. This part's incorrect. So we say 100, 90, and then also small names is, yeah, so if x is not equal to oh, I see. Oh, that's interesting. So if it's smaller, you just immediately return small names of x. Now that's kind of tricky too, actually, because you don't know what you added here. So you want to add ret. Yeah, this logic is faulty. Something here is missing. 900, there should be 99,000. So greater than 99, do that. If you're not, now here we're greater than or equal to the initial name, so 90. So add larger names. Modulo 10. If we're not 0, excuse me, add a space plus small names of x. Something like this. And yeah, otherwise, right. Something like this. 909,000. All right. So this is 0, goes to 10, 1, 20. Oh, I see. So actually, I need to add 1 to whatever this is. So divide by 100. No. Excuse me. When you take this modulo, so you take 999 modulo 100 puts you at 99. This should be 99. You would say 99 divided by 10. Excuse me, is 9. This should be 90. This is 0. Oh, excuse me. Whoa. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this should actually be an error here. I think you subtract 1. Oh, that's a, what do they call that? That's an index out of bounds error. That doesn't get caught. That's actually a over, what do they call that? An over, there's a name for that. That's called a buffer overflow error. Excuse me. Okay, that works. That works as expected. Yeah, interesting. Brother, there's so much stuff involved here. There's so many things going on here. How long did that take us? It's almost an hour, yeah. I don't think we're necessarily correct, but I mean, we could be like fairly confident with these test cases. We could take some random, take like 10, excuse me, 10,000 random numbers. 1 and, oh, I want 10,000. We're going to rand range 31 minus 1. I think that's what we want. Excuse me. Excuse me. See how long how we do here. It's also 10,000 numbers. Ooh, one of them's wrong. Oof. Which one would it be that's wrong though? I have 10,000 numbers. How do we figure out which one's wrong? This could be a while, huh? Oh, I have no idea. You maybe take a diff. Could do it that way. That works. So we can say vim a. Oh. Oh yeah. Okay. A.exe we don't want. So temp a. Oh, that's a lot. It's going. Woo! Okay. Is there a faster way to do this? I don't think so. Could do another one. No kidding. Okay. They're both going. Got 10,000 lines of text to paste. We can find our where we went wrong. Somewhere in there, something is wrong. Who knows, man? Yeah, there's like so many test cases. There's so many. I don't know. What could it be? Got a 2 Sigma terminal just pasting away. Oh, it's funny. All right. Let's go to our temporary Python file, and let's do 100 numbers in the range from 1 to like 10,000, something like 10,000. You know what could have happened? I could have had an error where these are fine. Yeah, no, I don't know. Python temp py tt. Oh, I should have done that. Oh, that was a mistake. Yeah, I was supposed to do that. That's okay. Like 1,000 numbers or something. I forgot what we picked here. Hopefully we can find the error somewhere in the smaller data set. That's what I'm looking for. Nope. 10,000 look okay, I guess. What did we? Yeah. All right. Let's do 100 from. 1, 2, 3, 4, 5, 6, 10 million. I want to test 0 in here somewhere. Okay, I got this one. So that's temp A. Temp B is still going. Oh, we got a wrong answer. Okay, that's good. It's not good, but at least this was a smaller data set to work with here. Excuse me. I don't know what's going on with my throat. Which one's wrong? The other one's still going. I go through 100 of these, kind of slow, huh? Oh, I don't see it. I don't see the error. Okay. Hope I have diff. Okay. Oh, 100, 0, 1,000. You probably see that a few times. Yeah, the 0 is just added in random spots. Ah, there you go. Okay. It's kind of a slight thing. 376,629,900 0. Okay, where is that being added? Is that because of this one? Oh, yeah, that's tricky. That's really tricky. If it's not 0, actually, if it's 0, we should just return immediately. Yeah. Well, the problem with this is that we don't really handle 0 correctly, right? We could just say if the number is 0 and then just not handle 0 and under 1,000. Right, we can handle 0 here. Because we use 0 to figure out like whether or not we should add more things. So if it's not 0, we would add, but the problem is if it is 0 here, then yeah, that's really tricky. Yeah, I'll just add an edge case here. If it's 0, and then otherwise we say If it's greater than or equal to this number, then we do that. Otherwise, say if x is greater than or equal to 1, then we add that value there. Don't arbitrarily add zeros. There we go. Okay. We deleted the original, the one that we had issues on before. Yeah, there's always some subtle thing. Let's do 1,000 numbers between the range of 1 and 2 to the 31st minus 1. Okay, we can close these. I think we got it. Oh, okay. Let's do another round. For good measure. Could do like the first 10,000 numbers also. I think we got it. I think we're okay. Let's do 10,000 and we'll just print x. See if we handle sort of the transitions correctly. Some of the transitions. All right, I think we got it. We're gonna go for it. I don't know. It's hard to test everything, but it's we can be somewhat confident. Oh, there we go. Okay, not bad. I'm gonna submit that 10 times for good measure. Oh, interesting. So the first time we got 100%, and then after that, all right. How do we do? So, yeah, that's pretty much it. Don't mind me while I submit it 100 times to pad my score. Okay, so yeah, I mean, there's not a lot to say about this question other than this is like a really obnoxious question, and you definitely want to test a bunch. That's why it's obnoxious, is because there's so many pieces to it. A lot of if-else's and getting this sort of what's the word? Getting this formatted correctly. So one idea would be to, like, I kind of just littered all these if statements in here with these spaces, but we could have created a, it's kind of better to do it this way, use a little bit less memory, but like another approach would be to add, like, just put the pieces together into an array, the pieces that you know you're going to need, without these spaces, and then format later using like a join routine, like write a join routine. And a join routine would just take each string and put a space between them, except the last string, or wouldn't have a space to the left of the first string. And so you can join all the names, and then you could have sort of a, you could do it that way too. That's maybe better than what I did in terms of like how simple it would be. Like if you wanted to code this fast, if you wanted to code this quickly, you could, if you wanted to code this quickly, you could add what I was describing. You still have, but you don't really have that many more if statements to just add the spaces. There's only really one here. here, but you had this anyway. 1 here. Yeah, it's only like 1 extra if statement, 2 extra if statements for the spaces, so you really wouldn't be saving yourself that much. I do think it's easier to have an edge case for zeros though. I have 2 edge cases here because it's just like way too complicated to go through this routine. So it's like it's not the cleanest code, not very clean. So here, what happens? If this num was 0, what would happen here? It wouldn't even enter this loop, so you do need an edge case here. And then also you have another edge case because handling 0 in this logic doesn't really work too nicely also. Excuse me. Yeah, because the problem is you don't know how to handle like 900 versus 0, because if you try to add a 0 here and you have like 900 handled, you don't necessarily know whether or not you should enter this here. Whereas so you kind of have an awkward thing if you don't handle 0. Excuse me. There's probably a cleaner way to do this, quite frankly, but we're not gonna go crazy. We're not gonna try to get into all that. Try to figure out how to do it more cleanly. I would say like it's fine. You know, this is like gonna be messy no matter how you do it. Somewhat messy. It's kind of why it's a LeetCode hard and why it has like took me an hour to do it. Is that it's just so many pieces, and the test cases and the pieces, and I'm pretty sure I've seen this question before too. Yeah, you can handle the under 1,000 and then break it up into 1,000 pieces and then add a descriptor. So that's the basic logic, is that you break it up into thousands and then add a description after each 1,000, right? For billion, million, thousand, build from left to right. And then you only add a space and potentially add something else if the next number is not 0. And then you handle the under 1,000 in a special way. Also, you need to have an edge case for just 0. The under 1,000 works nicely, so you have an edge case to handle the 0 here, and another edge case in the under 1,000 for 0. And then you can just break this into the digit in the hundreds column, and then the rest of it can be processed with a with some logic where you would, if you're 0, you skip this altogether after you process the hundreds. If you're not 0 though, you can say you can just directly state what the number is, which gets added to your hundreds, right, after the hundreds. And then if you would handle the tens and the digits if you're too large for sort of the initial values, and then if you're not too large for the initial values, then you just add the initial values, and you assume that you already have a space or don't have a space if you don't need it. Yeah. So, and that these are sort of self-contained in that they don't add or remove spaces from the beginning or the end, so you can handle outside of that, adding and removing spaces in the under 1,000. And the descriptors, you always just have a space. You could actually remove the space here and add a space here for the descriptors. That might be better. Let me do that. I think that's still correct if we do this. Is that still correct? That might not be correct. I think it's still correct. Yeah, because T is going to go to, oh, okay. It's accepted. Empty string. Oh no! Oh! Oh! That hurts. Ouch. Nope. Don't want to add that. Don't want to do it that way. You do want to have the empty descriptor. Yeah. That's my mistake. I didn't think about that. Ooh. That's awkward. I should have tested that. Ooh. Wow. That's kind of a subtle thing. But yeah, the empty descriptor when I is 0 at the end, I didn't even think about that. That's so I get for spamming. All right. I should have thought about that. Could have gone through the test cases first. Yeah, that would have been good instead of just submitting it. How do you handle that? Yeah, that's a subtle thing. That's actually really subtle too. So only if there is something to the right do you add a space. Right, because if you're just under 1,000, then you'll end up adding an arbitrary oh wow, that's super subtle. I didn't realize that. Whoops. Whoops. Alright, well, we got a few right and another one wrong, so alright, I'm gonna go here. I think it's probably it for me. I'm gonna hit the button a couple more times though. So thank you for watching. I'll talk to you soon. Have a good rest of your day. Interesting question, kind of hard, kind of challenging. I definitely struggled. That took a while. Like this, ideally you'd want to do this pretty quickly, but I don't know if I could do this really quickly. Like the logic is just kind of all over the place, like just naturally. I see why a lot of people downloaded this too. It's for the same reason. Yeah, I guess that's it. I guess that's it. Okay, that's fine. That's fine. All right. Thank you for watching. Talk to you soon.